Welcome. This question says a positive 3 Coulomb point charge is located at 2i plus 3j plus 4k meters. So I'm given the ijk address in 3 dimensions. A positive 12 Coulomb point charge is located at 3i plus 5j plus 1k meters. Again, an ijk address which is in 3 dimensions. And what is the vector force experienced by the 3 Coulomb point charge? So let me draw some, let's visualize this first of all. So I'm going to draw this. This is my y, and this is my x, and this is my z. Those are my axes. And then let's do a bit of color coding here. So let's make this the 3 Coulomb in green, so I can make my diagram a little bit more straightforward. So this is +1, +2, and then 1, 2, 3. So if I go dot, 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 and then it's going to be +4. So we have 1, 2, 3, 4. So with a bit of practice, you can create drawings like this, and you don't draw them very often, but I think it's really useful to get this skill, because visualization helps tremendously. So can you see how this guy here, this is my 3 Coulomb positive. So there's my 3 Coulomb positive charge. It's kind of like sticking out towards me. And then let's do one in blue, I guess. And so this is going to be my 12 Coulomb, and this is going to be located there. And this is going to be 3 x's, 3 i's, and then 5. Oh, I hope I get room for this. So 5 is, I just about made it. So that's my x and my y, and then only 1 forward, so we're just taking 1 step forward. That's plus 12 coulombs. So for some people, they find that, you know, it kind of expresses a lot to them, and other people, they're just not so practiced as yet. But as everything, if you practice, it will get easier. So I'm just making up these like boxes, and I'm trying to visualize where my point charge is. You don't have to be able to do these boxes, but I personally think it really helps if you can do these. I'm just drawing them in a solid line just in case that makes it a little bit more visualized. You can visualize it better. Okay. The key thing is, I guess, is that my force, these guys are going to repel each other, so my force on the 3 is going to be like that. There's my F on my 3. Fe on my 3. So it's the force is going to be pushing away like that. So he wants to know what is the vector force. So I need to be able to specify this vector in terms of its magnitude and also in terms of its direction. So I've got a lot going on in this question. What's my expression? Well, my force electrostatic as a vector is equal to Ke, that's Coulomb's constant, and then I have, you know, one charge and then the other charge over the separation squared. That's what we've always had for the magnitude, but we have to have a multiplication by a unit vector, a vector which only has a magnitude of 1. So if I multiply this magnitude by 1, I don't change it, but it gives me my ijk information. Okay, so the beginning bit looks like it should be okay. So I'm going to say, well, Fe is equal to KE. I'm just going to leave KE as KE for a minute. I've got enough going on. And then this is plus 12, but I don't care about the sign. It's just 12 multiplied by, this is 3, so don't care about that. And now I have to do my R squared. And my R squared is that separation squared. Okay, so let's visualize a little bit more. I'm going to imagine just having my origin, and I'm going to have my blue vector. I'm going to draw it in one plane. So there's my blue vector. And what is the blue vector? It's basically, oh, disappeared on me, didn't it? What is my blue vector? It is 3i plus 5j plus 1k meters. And then let's now imagine my green vector. And this is going to be, what would that be? That would be, my green vector is 2i plus 3j plus 4k meters. Now, let's look at my diagram. I'm looking for the force experienced by this 3 Coulomb charge, which is the 3 vector. I'm going to just cheat a little bit just to make my diagram look a bit better. And that force, so here's the 3 and here's the 12 Coulomb, so that force is in that direction. So there's my Fe on the 3, and I'm looking for that separation. Well, I'm looking for a really vector which goes in that direction. So this would be my vector for my separation. Now let's think about vector addition. The blue vector plus the black vector equals the green vector. So let's do that. Let's call this, so let's go, I'm trying to find a way I can express this. So it's going to be the blue vector displacement added to the black vector displacement equals the green vector. Do you see that from the vector diagram? If you were drawing vector diagrams, that arrow added, put the tail of the second vector on the head of the first vector, plus the black vector, gives me a resultant, which is the green vector. So that's what I've written down here. So I want the black vector. So the black vector is equal to, well, the green vector stays where it is. So we have the green vector, and then I subtract from that my blue vector. Yes. So I need to set it myself a little grid. So I have I, J, K, and I go, okay, I need my green vector. And my green vector is 2i plus 3j plus 4k. Let's put those as positive signs. So I got that from over here. And then I'm going to subtract from that well, you know, I'm going to be a bit careful. I'm going to add the opposite. Subtracting the blue vector is like adding the negative of the blue vector. So rather than having +3, I'm going to have -3. Rather than having +5, I'm going to have -5. And rather than having +1, I'm going to have -1. So hopefully when you did vectors, you got used to the idea of subtracting a vector is like adding the opposite, the negative of the original vector. Because what I find is if I try and subtract, people will tend to subtract the first one and then they'll just add the rest. But I want to make sure I treat all these the same. So my experience is if you add the negative, people make fewer mistakes. So then this is going to be, of course, the black vector, which is -1i, -5, -2j, and then +3k. So that is the vector which goes from the 12 Coulomb charge to the 3 Coulomb charge. That's the vector. I just worked that vector out. So to keep life simple, we're gonna kind of give ourselves some space here. Okay, so then big deal. What do I do now? Well, here's the thing. I want to find the magnitude of this vector and square it. So I'm going to say, well, this is Pythagoras. So I go -1 squared plus -2 squared plus 3 squared. That's almost magnitude. I got to square root that because, you know, the square root of a squared plus b squared plus c squared equals d squared in 3 dimensions. But I can't forget that this is r squared. This is r. It is the magnitude of this vector r, and we get it by doing the square root of each coefficient squared. But if I want to get r squared, I've got to square that. Okay? It's just practice. And then the next thing I do is I go to, so I found my r squared, so I got my magnitude. Now I've got to find the sky. And of course, because I looked at my diagram and because I was careful to do this the right way around, the direction I want is -1i -2j plus 3k. That is the vector which goes from the 12 Coulomb to the 3 Coulomb in that direction. But it's not a unit vector because it's too long. It should have a magnitude of 1, but it's got a magnitude of something else. So how can we make it have a magnitude of 1? We make it have a magnitude of 1 by dividing it by its own magnitude, which would be, well, it's going to be -1 squared plus -2 squared plus 3 squared, square rooted. That is the magnitude. That's how we found this r. R is the magnitude of the separation. The separation is given by the vector going between the two charges divided by the distance. If you actually leave it in this shape, I can actually tell very quickly if you know what you're doing. But it's nice to tidy up. So this equals 12 threes are 36 ke over. And let's have a look. That's going to be 1 plus 4 is 5 plus 9. So that's going to be 14. It's going to be the square root of 14 squared because it's r squared. And this is multiplied by -1i minus 2j plus 3k, and this is divided by, well, that's also going to be the square root of 14. And actually, if you put brackets around that and note down that the units are newtons, that is a decent answer. That is a decent answer in a test, because I can see that you know what you're doing. If you wanted to work it out, longhand, then you would say, well, FE, I'm not sure I'm going to go all the way because this is getting a bit long, but it would be 36 KE over 14, which is a number, multiplied into minus 1I minus 2j plus 3k over the square root of 14 newtons. And you can work out this number and multiply it into that and get so many I, and then get so many j and get so many k, and just end up with numbers in the end. But I choose not to go that far. So there's a lot going on here, but it's a lot of things that we've done in the past. So we started off with an address for my 3 Coulomb charge, and we had an address for my 12 Coulomb charge. And we recognized that the force experienced by, in this case, it's the 3 Coulomb charge, is going to be KE times the big charge times the little charge over the separation squared, which is a magnitude, multiplied by the unit vector which points in the appropriate direction. And because these are both positives, it's going to be a vector which is pointing away, pointing from the 12 towards the 3, because it's a repulsive force. And then what I do is I basically say, okay, well, I need to get this, I need to start writing it out, and I find I don't have my separation obviously given to me. So then I basically, somewhat carefully, I draw a vector representing from the origin to the address of the 12 Coulomb. I draw a vector from the origin representing the address of the 3 Coulomb. And then I say, well, I want to go from the 12 to the 3, so I'd make sure my arrow is in the right direction, because that is the direction of this force that I'm interested in, because it's a repulsive force. And then I'm doing vectors. So I say, oh, the blue plus the black equals the green, so blue plus black equals green, so black equals green minus blue, and the green vector was plus 2 plus 3 plus 4. And then I add, rather than subtracting the blue vector, I could do, but rather than subtracting it, I've learned to add the opposite of the blue. So it's minus 3 rather than plus 3i, minus 5 rather than plus 5j, and minus 1 rather than plus 1k. And I do my math, and I get minus 1i minus 2j plus 3k. That's the vector which goes from the 12 to the 3 Coulomb vector. Now, given this vector, I can actually work out its magnitude, which gives me the separation by just remembering Pythagoras. The magnitude is equal to the square root of the first coefficient squared plus the second coefficient squared plus the third coefficient squared. So that would be minus 1 squared plus minus 2 squared plus 3 squared. Square root it gets me my separation, but I've got to remember that this is r squared. I've got to remember that that is r squared. People forget that. So I've got to remember that I've got to square this. So there's my magnitude. Now I just need this unit vector pointing in the right direction. Well, I already know a vector that goes from the 12 to the 3. I've already got that vector. I worked it out down here. And if I can simply take this vector, which is too big, and divide it by its own magnitude, then I get the unit vector. So that's minus 1i minus 2j plus 3k and it's divided by its own magnitude. And again, its own magnitude is the square root of the first coefficient squared plus the second coefficient squared plus the third coefficient squared. It's square rooted and there's not this squared term over here, so it's just square rooted this time. And then I simply say, well, let's clean up a bit. So 1 squared, 1 plus 4 plus 9 is equal to 14. So this is the square root of 14 squared, which is 14. And over here, this is the square root of 14. Common mistakes, people forget the units. They've kind of like done a whole bunch of letters, so they don't think units are on their mind, and yet you got to do your units. It's still got to be said to be in newtons. And then the other common mistake is people forget this squared term here. A very common mistake is people are just not comfortable with this visualization, and so they get the wrong sign. They have just, plus 1, plus 2, minus 3. It's the opposite direction. They get the direction wrong. But there's, if you think about it, we just worked out the vector force between two charges in three-dimensional space, and that's not bad, is it? I think that's a pretty good thing to do. So there we have it.